So now we are gonna have a talk given by Andrés Ospina from UTP. The talk is gonna be about harmonic sp2 invariant G2 structures on the 7 sphere. So thank you, Andrés, for being here with us, and you can start if you want.
Thank you for the organizers for accepting my proposal. It's nice to be here again. I have nice memories from Brasilia. So today, as Eder said, I will talk about harmonic sp2 invariant G2 structures on the 7 sphere. Basically, this was a joint work with Eric Louveau from Brest and Enrique Saerb and Juliette Saavedra from Campinas. So the main goals from this work was to try to describe the sp2 invariant G2 structures and the induced Riemannian metrics for these G2 structures for the 7 sphere, given as the quotient of the symplectic group, the compact group. So with the description, we try to study a natural geometric flow on G2 geometry, and obtaining the some particular properties of this geometric flow. The next natural question was to study the stability of the limit points or the critical points of this geometric flow. A lot of the concepts in this talk, you can see the relation with the previous talk of Professor Lauret, Professor Lucas, and even the previous talk of Professor Lino. So the outline of the talk is basically these points. I would try to give some preliminaries and some concepts about G2 geometry. Next, I will try to explain how we describe the sp2 invariant G2 structure on the 7 sphere using the homogeneous geometry of the sphere. Then we define what it means isometric G2 structures, and finally we study the concept of harmonicity and stability for these G2 structures. And the last part is just some comments about some remarks and future questions in this topic. Okay, so about G2 geometry, we now to consider a G2 structure as a positive differential free form on the manifold. The word positive here means that the free form induce a bilinear form here, which is this bilinear form is positive defined, right? Maybe this for our proposals is this is the better definition, but there is a lot of definition of G2 structures. One of the definition is that it's a free form which is invariant by the action of the Lie group G2. Perhaps from that definition comes the word G2 structure, right? Because it's involved with the Lie group G2. And the important thing with our definition is that this bilinear form B induce a Riemannian metric in this way, like an equation 2. This relation is a non-linear relation, so it's not easy to compute in any case. But the important thing is that the three form phi describe the Riemannian metric itself. So save this in mind, that given a G2 structure, you always have a Riemannian metric induced by this G2 structure, right? Another important geometric structure induced by the G2 structure, by the tree form, is a cross product on the tangent bundle. The definition is using, of course, the tree form. And maybe an important remark here is that this cross product is defined in a smooth way on each point of the manifold on the tangent space. So you have for each point you have because the manifold has dimension 7, you have an identification with R7, which is also can also be identified with the imaginary part of the octonion algebra. So using the product of the algebra, you can define a cross product, a canonical cross product, like A times B is equal to the imaginary part of A times B using the algebra product. And in this way, you can define also a G2 structure as a cross product, which is related in each point in a smooth way with the canonical cross product of the octonions. You can think in this cross product like the construction of the cross product of R3 using the quaternionic product, right? So, but okay. So with that, using the metric induced by the tree form, we have volume form and a Hodge-star operator and a Riemannian connection. The Riemannian connection is important because with that, if the G2 structure is parallel with respect to this Riemannian connection, this is equivalent with that the holonomy of the metric is contained in G2. We saw the last week the talk of Professor Adrian about holonomy of groups, and manifolds with when the free form satisfies this non-linear PDE, the free form is called torsion free, and the corresponding manifold endowed with this free form, with this torsion free G2 structure, is called G2 manifold. In particular, G2 manifold are Ricci flat, and the most important problem in G2 geometry is try to construct G2 manifolds. This means metrics with holonomy containing in G2. But the problem is that it implies to solve a nonlinear PDE. So maybe one option is try to relax the condition of the torsion to be 0. So that arise another classes of G2 structures, which are G2 structures with torsion. And some examples of this G2 structure is the closed G2 structures, the co-closed G2 structures, and the harmonic G2 structures. Sometimes these harmonic G2 structures are called free divergence for obvious reasons. But in this talk, we call as harmonic because we will see that they arise from a harmonic problem, like the harmonic map problem. And so using this G2 structure with torsion, an alternative approach for the study of G2 geometry is the study of geometric flows, right? Maybe inspired by the Ricci flow. So we have some examples: the Laplacian flow, the Laplacian coflow, and the harmonic flow. Those all of these geometric flows are PDEs on the space of forms. So in some cases there is short time existence, in other cases there is not, and some questions as long time existence and convergence are still open questions. But for the case of the harmonic flow, this PDE, this geometric flow equation, can be seen as the gradient flow of energy and the gradient flow of energy functional. That's why, and if you see, you can see the torsion as the tension field of a map, as in the theory of harmonic maps, and the critical points, which will be the second fundamental form of the harmonic map. In this case, the harmonic map will be our 3 form, our G2 structure. The critical points are exactly the harmonic G2 structures. And an important property of this flow in relation with the other flows is that for a solution of the harmonic flow, the metric remains the same, yes? Because if you have a solution, for each solution, you have a Riemannian metric associated with this G2 structure for each T. But the important thing here is that it remains constant. So for a solution of the harmonic flow, always you have the same metric. So you fix the metric. And in our work, we work with a homogeneous space. So as we see on the talk about Ricci flow, the PDE becomes an ODE if you try to solve the problem of the geometric flow restricted to the invariant structures. So with this property, we have short time existence, and we could prove another properties of the flow. So with that, we focus on the case of the 7x sphere given in this way. And as you do all the things that Professor Lino said in the previous talk, you have isotropy decomposition into irreducible submodules, invariants by the action of the adjoint representation. But the key point here is that you can describe the invariant G2 structures as the invariant 3 forms on the isotropy representation, which are invariant by the adjoint representation. So using this description, we just fix a basis for the isotropy representation. We fix this two forms for this subspace P4, which has dimension 4, and we can compute all the invariant G2 structures, which depends of 10 parameters, and using these 10 parameters can be gathered in this condition, which give us that the condition that the tree form is positive, as we defined previously. And the important thing is that we can construct the induced Riemannian, the induced inner product, right? And we have that in this case, we don't have a diagonal matrix because we have equivalent submodules in the isotropy representation, right? So this result was proved previously by Reidegel and Van Leeuwen-Mounier, but it was using infinitesimal arguments. It means that they just give these numbers for the case of the 7th sphere. In our solution, we obtain explicitly the free form, the G2 structure, and the induced metric. And using this parameterization, we can describe the space of invariant G2 structures as this homogeneous space. Of course, if we fix an orientation, a positive orientation, because it just depends of the parameter A. And also, we can describe the space of invariant inner products as this homogeneous space. A curious application of this last identification is that we can endow the space of metrics with an invariant G2 structures, because in fact this quotient can be identified with this solved manifold. But okay, so with this description, we define what it means isometric G2 structures. We say that two G2 structures are isometric if they have the same induced metric and orientation, right? And we denote the class of the isometric class of a G2 structure in this way. It means this is the set of all the G2 structures with the same Riemannian metric and orientation. And using classification of Ziller about the invariant sp2 metrics on the 7th sphere up to isometry, he proved that these 7 parameters, this 7-parameter family falls in 4 parameters just. So, which are in fact the eigenvalues of the symmetric positive matrix that defines your inner product. So with our approach, we have that this reduction given by Ziller can be interpreted in this way, with an action on of the group SO3 on the left side of our homogeneous manifold, which is basically the product of the positive 4 copies of the positive real numbers, which are exactly the eigenvalues of the matrix that defines your inner product, right? And you can obtain the same thing with the space of invariant G2 structures, which is basically the product of these two sets, right? These two manifolds. So using these last descriptions, we use these two last descriptions to define the G2 structures and the metric. So in coordinates or a basis for the, or if you fix a basis for the isotropy representation, you have these two expressions. The next step will be try to put these three form into the geometric flow equation, but the equations that you obtain are really big and difficult to solve, even if it's an ODE. Maybe there is no an explicit solution. So the alternative way to try to solve this geometric flow was to use the Bryant's formula, which describe all the isometric G2 structures, which are with the same associated metric and orientation. All the isometric G2 structures are parameterized by a function and a vector field. Sorry. Oh, shit. So you use just a function and a vector field, and this equation defines for you all the parameterize all the geometric, all the isometric G2 structures. So you have phi 2 in terms of phi, or the Hodge, the dual four form of phi, which is 44, and some operations that involve the vector field and the function. All this guy in the right side is it's a free form. And the important thing here, you have a lot of remarks about that, is that in the case of invariant G2 structures, if they are isometric, this pair is exactly invariant. It means that f is an invariant function and x is an invariant vector field. So an invariant function, you have exactly a constant function, and you just need to study the invariant vector fields on your manifold if you want to find a solution of the geometric flow. So that thing is that we did for the case of a particular metric. We call the ansatz case. We consider this particular metric, which is given just by one parameter. For this metric, for this inner product, you have an associated family of isometric G2 structure using the Bryant's formula, where the vector field and the function is H0, just one parameter, and the vector field is given by this subspace of the, is given by a vector in this subspace of the isotropy representation, this vector x. In fact, these parameters, each 0, each 1, each 2, and each 3 is a unitary quaternion. So using this description, you can compute the divergence of the full torsion tensor, and you obtain this expression in terms of the parameter R and the parameters of the unitary quaternion. And with this equation 3, you can describe the harmonic, in fact, the harmonic G2 structures on the isometric class, because this is the case when the divergence of the torsion is equal to 0. So that it was the first result. If you identify the unitary quaternions with the three-dimensional sphere, and you define these subsets that we call S2 could be interpreted as the equator of S3, and this set will be like the poles of the 3-sphere. You can describe the critical points of this energy functional, which are the G2 structures that satisfy this divergence condition, free divergence condition. So the critical points are these families, right? Because of the equation, right? It's 0 when R is equal to 1, and it's 0 when H2 is equal to 0, or the other cases, the other 3 components are 0. Okay, so with this description of the critical points, we try to study the harmonic flow, the corresponding gradient flow of the energy functional. But as I said, it was very difficult. So we tried to use this alternative approach, which is to try to solve the evolution of the pair of the function and the vector field.
Andrés?
Yes?
So I'm sorry to bother you. You have 3 minutes, okay?
Okay, it's okay. Sorry. So basically, we try to define, to solve this equation. For that, we obtain a linear, using our description for the divergence, we obtain this system of ODEs 4. The solution we can obtain explicitly. The best thing here is that the flow in this case is eternal. The solution is eternal, and on the limit points, they converge to harmonic G2 structures, which are in fact in the sets that we described previously of the harmonic G2 structures. The limit points are there, and the behavior depends of the value of R, if it's greater or lower than 1, right? And you can do, with this, you can try to study the second variation and obtain stability conditions, but you just can obtain some results about the unstable. As Jorge said in his talk, you don't know, it's difficult to compute whole the spectrum of the second variation operator. So you can just use the invariant setting to prove something about instability. So I have some questions, but my time is over. So sorry, and thanks for the attention.
Okay, let's thank. So questions or comments? So I have a question, Andrés. So how can
Yes.
I mean, is there any relation between this homogeneous invariant, actually, G2 structures with the underlying Trisazakian structures which we have in the sphere, the S7 sphere?
Yes, because in fact, when you try when you apply this ansat, right, you have a one parameter family of metrics, right? So for a particular cases of this value R, you obtain the Rom sphere and the squash sphere, which I think that they are the only examples of Trisazakian, right?
Okay, but the G2 structure is H-flat?
No, it's not Ricci flat. No,
Is
it's
Sasaki-Einstein structure?
yeah, they are Sasakian Einstein structures, but they have torsion. The G2 structures have torsion, but it's a well-behaved torsion. It's something that some people call nearly parallel G2 structures.
Okay.
And these G2 structures are, in fact, critical points of the energy functional. And one thing that is, I don't know how to explain that, but that two cases that you say, the instant Sasakian, the three Sasakian, and the instant Sasakian, in this case, in these ansatz, they are stable critical points. But yes, they are inside these ansatz.
Okay. So more questions or comments?
So did you get local minima?
Yes. Yes. Let me show you the last.
Yeah, and I'd like to see the questions on stability you mentioned.
Yes, you have the family of your critical points, right? So you have the corresponding torsion for this family of critical points, and you compute in these three cases the second variation, and the positivity of the negative of this second variation will be depend of the value of R. So the conclusion is that you have depending of if R is lower than 1 or greater than 1, you have your critical point is stable, G stable, or unstable. But you obtain local minima under invariant variation, just invariant variation, right?
Are these global minima and global maxima?
No, I don't know if they are.
Okay. And what about the questions you mentioned?
Perhaps I don't know. Perhaps the nearly parallel case, they are global minima, because you can simplify this equation when the G2 structure is nearly parallel. So you can always prove that this Hessian of the energy function is always non-negative, right? So in the
That's
case
very
of
nice.
what?
That's very nice. That's very
Yeah,
nice.
yeah.
Okay.
Yes. So one question could be try to say the thing to do the same thing that you did for the case of Einstein metrics. How to describe this operator on the homogeneous case? Perhaps it could be simpler than the general operator, because you have these tensors here on the equation phi. Another question is if this equation phi simplifies for some classes of G2 structures. For example, for the nearly parallel case, the equation it's simpler. So maybe for the co-closed case or locally conformal closed G2 structure, I don't know. There are a lot of classes. And the last question is, what about in other examples? For example, the Alof-Wallach space or the Stiefel manifold, where you can do this. Can you repeat all this computation in these cases? I don't know. Maybe could be something interesting.
Okay, thanks.
You're welcome.
So more questions or comments? Okay, let's thank you, Andrés, again.